Welcome to my lesson, Performing 2D Vector Addition. In this video, I will demonstrate how resolving vectors into horizontal and vertical components allow you to add two or more vectors together. So what's the process? First of all, resolve each vector into its horizontal and vertical components. Then add up all of the horizontal components together, and then separately add up all of the vertical components. That will give you the horizontal and vertical components of the resultant vector. Then use Pythagoras' theorem to determine the magnitude of the resultant vector, and trigonometry to determine the direction that the resultant vector will act in. So let's say we're adding these two vectors together. First of all, let's draw a diagram of what's going on so we can clearly see the math working together. In fact, I would suggest always draw a diagram if you can. If you've got the space, draw a diagram. If you've got the time, draw a diagram. So let's resolve both of these vectors. The 12 Newton vector and the 20 Newton vector. The horizontal component of the 12 Newton vector will be 12 cosine 45 degrees to the right. Direction's important here because we're dealing with vectors, and when we add up the component vectors, they can either add up to support each other, or they can partially cancel each other out. So you need to keep in mind we have to consider the directions as well. And the vertical component of the 12 Newton vector will be 12 sine 45 degrees upwards. Similarly, for the 20 Newton vector, it'll be 20 cosine 30 degrees to the left and 20 sine 30 degrees upwards. Which means that the resultant vector, or the horizontal component of the resultant vector, will be 20 cosine 30 degrees minus 12 cosine 45 degrees to the left, which is 8.84 newtons to the left. And for the vertical component, it will be 12 sine 45 degrees plus 20 sine 30 degrees, which will be 18.49 newtons upwards. So now we have the horizontal and vertical components of the resultant vector. We can use Pythagoras. First of all, let's draw up what the resultant vector is going to look like with our horizontal and vertical components. Be like that. Now we can use Pythagoras' theorem to determine the magnitude of that resultant vector. We have a root of 8.84 squared plus 18.49 squared, which will be 20.49 newtons. As for the direction, let's put an angle theta in. We'll use that theta to determine, or we'll use it to give us a bearing for our direction. So tan theta is our opposite over adjacent. Now the reason I'm using tan theta and not sine or cosine theta is when we calculated our magnitude, we did rounding, which means our horizontal and vertical components are going to be more precise, they're going to be more accurate. That's the difference between precision and accuracy. Precision is like how many digit places you go to. Accuracy is how accurate your result is, how close it is to what its actual value is. For all intended purposes for this video, I'm just going to say that the magnitude value is going to be less accurate than the horizontal and vertical components as a result of rounding. Anyway, that's why we're using tan theta. Sine theta, cosine theta does work, but you might get a slightly different answer. Slightly less accurate answer. So tan theta is opposite over adjacent. Theta is the tan inverse of 18.49 over 8.84, which is 64.45 degrees. So we have a magnitude of our resultant vector, and we have a direction it's acting in. Let's look at this question now. Jim walks 45 meters north, 30 degrees east. Then he walks a further 20 meters east. What is his overall displacement vector? First thing we want to do is draw a diagram of the situation. We have a word question. We want to understand what math we need to perform. So that'll look like this. And the resultant vector will look like that. Now let's resolve the 45 meter vector into its horizontal and vertical components. which will be 45 cosine 60 degrees to the east, and 45 sine 60 degrees upwards. Now it's worth mentioning that the 20 meter vector is acting towards the east, which means that if we were to resolve that, it would have a vertical component of 0. So I'm not going to bother resolving it. So yeah, for the horizontal component of our resultant vector will be 20 plus 45 cosine 60 degrees, which is 42.5 meters to the east. And the vertical component of our resultant vector is just going to be 45 sine 60 degrees, which is 38.97 meters north. So now we have the horizontal and vertical components of the resultant vector. We can use Pythagoras' theorem to determine the magnitude of the displacement. Square root of 42.5 squared plus 38.97 squared, which will be 57.66 meters. Then we're trying to work out the direction it's going to be acting in. First of all, we're going to work out theta, the angle inside, and then we'll try to work out a form which is comparable to the angle or the direction that we were given in that question. So theta is tan inverse of 38.97 over 42.5, which is 42.52 degrees. In the question, we were given it in the form of north something degrees east. So in response, we should give it in a similar form, not just the angle of 42.52 degrees. So we'll go north and whatever angle to the east, to the west, or south, whatever angle to the east or to the west. That is the form that we are looking for. So we want that angle there, which is the complement of 42.52 degrees. So 90 minus 42.52 degrees is 47.48 degrees. So therefore, the overall displacement vector is 57.66 meters at 47.4 at north 47.48 degrees east. Thus, to conclude, two or more vectors can be added by resolving each vector into its horizontal and vertical components. Pythagoras' theorem can be used to determine the magnitude of the resultant vector, and trigonometry can be used to determine the direction that the resultant vector will act in. So that concludes my lessons for vectors for physics. I'm going to be moving on to projectile motion. Thanks for watching, and please feel free to subscribe.